There we go. Okay. I tried calling the Valentine system, it wouldn't connect. So you have that invitation and you're good. Are you all connected with your own computer then? Can you hear me there, Brittany?
Yes.
Excellent. Okay. Okay, let's go ahead and let's get started here. All right, so I had a few questions in my email about different problems on homework 3. In particular, trying to remember which one it was. Don't remember. It was the race car one. Where's the race car one? That one was certainly. Aha, yes. So we had a question, a couple of people asking questions about this one, and we had a couple of people asking questions about rearranging equations. I don't remember which, I think that was chapter 2 or chapter 3, I can't remember which. But you should know that if you do have questions, please go ahead and continue to ask your questions. And don't worry about it, even if the time expires in the homework. I'm willing to extend out the homework so you can finish the homework and try to get it as well understood as you possibly can. But let's take a look at this one right here. It starts off with this car accelerating from rest. It gives us initial velocity in the x direction or in the horizontal direction at rest. It accelerates along this length of the table, so it's giving us the distance or the delta x. Of its distance along the table that it moves. And then the first question they ask is when they give us the time, right? So they give us time, initial velocity, and distance. And they want to know what the acceleration is. And of course, there is a kinematic equation for that. We'll go and figure out what that is. Let's see here. We can either go to beginning of chapter 3 or we can go back into chapter 2 for that. Either way. Where is it? I can always struggle to find it here in this for some reason. Here we go. So if we have the initial velocity, we have the distance and the time, which equation can we use to find the acceleration? And it turns out to be this one right here. The distance is this thing inside the parentheses, the initial position, which in our case we would just call 0, subtracted from the final position. The final position would tell us that would be that distance that it travels. So the thing in parentheses would be the distance along the table that it travels. And then everything else we would, actually no, I'm lying to you, I'm sorry. This one requires the final velocity, which we don't have. We have to use this one. But it's the same thing, because when you subtract x minus x naught, that gives you the distance traveled along the table right here. Or you can just plug in x naught equals 0 and x is the distance along the table. And in this one, your initial velocity is 0 and it doesn't care about your final velocity. So then you just plug in the time here. So this second term is going to become 0. In the final term, you're going to solve for the time, or sorry, you're going to solve for the acceleration, and you're going to end up with 2 times the distance divided by the acceleration under the square root, divided by the square of time. So it'll be 2 times the 2 times distance divided by time squared will equal the acceleration. And that will get you part A. So this is the equation for part A. In part B, they want to know how fast it's going at the end. So you can, once you have the acceleration, you have your choice of equations you can use. You could use this one because you have both the initial position, the final position, and the time. Actually, that one is, yeah, that one would work for a constant. I'm trying to remember if this one will work if you're accelerating. This one will only work if you have the average velocity, which we don't. We only have the final velocity, so this one you can't use. But this one we can use because we have the time, we have the acceleration, and we have the initial velocity, so we can calculate the final velocity. And this one we can use because we have the initial velocity, the acceleration, and the change in distance. So you could use this one or this one. And in fact, you could even use, no, that one wouldn't help us. Yeah, so you can use either one of those, this one here or this one here to do that second part. And then they change it on you. They say, well, what if we put it off a ramp at the end? In this case, essentially the velocity that you're going to get from part B is going to be put in an angle. And the angle that they give you here may be different for each person. But you're going to now resolve it into components. And then you're going to solve it in 2 dimensions. How do we do that? Well, let's see here. Stop share, new share. Back to my terrible whiteboard skills with the mouse. I actually have a pad I should probably bring out here. Should work better. But anyway, in this case, we have our car going off at this angle. Whatever it is, we'll call it theta. And that means our velocity is at this angle, right? So our velocity now is at the angle theta with the x-axis, and we need to split it into 2 components. Velocity is whatever it is. This is going to be the velocity in the y direction. This is the velocity in the x direction. And because our angle theta is right next to the x direction component right here, v sub x, that's going to be a cosine thing. So you're going to take the tangent, sorry, not the tangent, they call this the hypotenuse, the longest side of the right triangle, right? Which is v. So you take the longest side of the right triangle and you multiply it by the cosine of the angle, and that will tell you the side that is closest to the angle, or this adjacent side right here. It's right next to the angle. And then the side that is opposite the angle, so the angle's here, but this is the opposite side of the triangle from there. That one you'll get by multiplying v times the sine of theta. Now, sine and cosine are just functions that your calculator knows how to calculate for given angles. And whatever your angle is, you just plug it in there, and you know what the v is. That's from part B. This comes from part B. So whatever the speed was that you calculated in part B, you plug it into these formulas, and then now you'll know how fast the car is going upward. That's Vy. And you'll know how fast the car is going forward. That's Vx. After this is kind of the tricky part. After this, you're going to use this one to figure out how much time the car is going to be in the air, because this is going to essentially tell you telling you how fast the ball is going up, and you know that gravity is going to pull it down and eventually make it hit the ground, right? This one, when you're done figuring out how much time it's in the air, you'll use this one to figure out the distance in x that it travels before it hits the ground. How do we do that? For the time one, what do we know we're going to split this up into two formulas. We're going to do the y direction first with x sub y, with this v sub y, And then we're going to do the x direction last. Sometimes you'll do it in the other way, it just depends on what you know. But in this case, with this one is going to tell us this is going to tell us how fast this thing is going in the y direction. In other words, it tells us the initial y direction velocity when we get this right here. This right here becomes the initial y direction velocity. And we're going to say that the top of the table, let's just assume, let's put up here this little table here. We'll assume that, you can assume the top of the table is y equals 0 if you want. Or you can assume the ground is y equals 0 and then the table is 1 meter above it or whatever it is for your problem. It doesn't matter. If you assume that this is y equals 0 right here, then your ground needs to be y equals negative whatever. You just need to make sure you do that if you make the tabletop y equals 0. But in either way, the problem tells you the distance between the table and the ground, I believe. Let's go back and check that really quick. Yeah, so in this problem, in mine, it tells me 1.8 meters, right? So it tells you the y distance between the table and the ground, and so we know our v0y. We're also going to know our y initial. We're going to know y0, and we're going to know y final. These three things we're going to know, right? We're going to know the initial velocity in the y direction. We're going to know y position initially. It'll either be 0 or it'll be some meters above the ground, however you choose your y dimension coordinates to be. And then the last thing that you're going to know is your acceleration. What's your acceleration in the y direction? In the up and down direction, what's our acceleration for projectile motion? I'll give you a clue. It's negative 9.8. Excellent. Meters per second squared. So, you have 4 things that you know, and now there's a kinematic equation that can tell you, for example, the time. For this one, it's that one that has the squared stuff in it, the time squared in it. You can use that. Yeah, so I would use that one, which looks like this. Y final equals y initial plus velocity initial in the y direction, which we know, times time, plus 1/2 a, where a is negative 9.8, times t squared. Now to solve this is a little bit messy because you're going to have to solve it using the quadratic formula, right? So it'll get a little bit messy. You'll get 2 answers in the end. One will be positive, one will be negative. You use the positive one. Once you've figured out t, then you're going to come over here. Once you've got t figured out, then you're going to come over here and you're going to say, well, what do I know in the x direction? In the x direction, I know the velocity in x, and I know that the velocity in x is a constant. I know what it is, and it's a constant. I calculated right here. So this comes down from here. And I know that it's constant, so I can use the first equation. The first kinematic equation, which says the final position in x equals the initial position in x plus the velocity in x times time. And you can calculate that final position in x, where how far it goes before it hits the ground. And this problem, more than any other problem, I think illustrates what we're doing in this chapter. It's just this over and over and over again, where we have some kind of movement, and it might be up and down, it might be side to side, but it might be somewhere in between, it might be a little bit of both. But we're going to use kinematic equations to figure it all out. And oftentimes, it's very easy to start with the y direction first when it's in 2 dimensions, when you're off at some angle. It's often easy to start in the y direction first because we know the acceleration in the y direction when it's projectile motion. That's one thing we already know. We know the acceleration is negative 9.8 meters per second squared. So that's just one less thing to figure out, right? So oftentimes it's first. Not always, but oftentimes. And then if you can figure out the time from that y direction, then you can jump over to the x direction, because in projectile motion in the x direction, as long as there's no friction or air resistance, this thing is just going to travel according to this equation. Or x equals, that's an x naught. Terrible. Oh, I promised myself I was going to figure out how to connect my iPad to Zoom so that I could draw these on the iPad and it would come up on this screen. But when I tried to do it, I failed and it was frustrating and I never figured it out. I have much better handwriting with my finger. So anyway, that is the car problem. Now, I haven't gone in and checked in Chapter 3 to see where you are all struggling, to see what problems are not completed. But does anybody have a problem from Chapter 3, another one that they'd like me to talk about a little bit and give you some direction on? It's extremely important that you keep things as clean and as organized as possible. And I know this isn't a great example of it, but you'll notice that I use big writing and I leave space in places. And I draw arrows and I circle things. It's important to keep things organized so that you don't get lost in what you're doing. Just keep that in mind. And I haven't done the calculations yet, but, well, at least not today. But when you're doing your calculations, also the same. Don't just plug it into your calculator and put an answer on the paper. Actually solve the equation so you can see that you've got it right. That will help you to learn and help you to get the problems correct also. Did you have a question from Chapter 3 at all?
Yeah.
What do you want to do?
I think it was 7.
Number 7 is rearranging this equation.
Yeah, so that one and then
Baseball thrown. Okay, let's do 7 really quick. So you want to? So which one does it ask you to solve for? Does it ask you to solve for x, or do you remember?
like,
Yeah.
it asks me to solve for a y.
For a sub y. Okay.
Yeah.
Let's do that then. Show you how that's done. We're doing problem 7. We're doing problem 7, and we're solving for the acceleration.
Okay, so it's kind of cutting out.
Is it really quiet on your end?
It's like, it was choppy.
Oh, it's choppy. That's just the internet connection, I suppose. I am recording this for YouTube, so I hope I'm recording it. Yes, I'm recording it for YouTube, so it should be available when we're done here. Sorry for the choppiness, but let's go ahead and do a clear all. So this is the equation. It's v final squared, and it can be sub x or sub y, it doesn't really matter. And then v initial squared plus 2 times the acceleration times the change in x, where they actually write out the change in x, right? They actually write it out as x final minus x initial, and that could be y final minus y initial, either way. But this equation, we're trying to solve for the a, right? So the key to solving equations in algebraic, these algebraic kind of questions, and this is quite important, so that you can solve for the answer first and then plug in the numbers. Create a formula, then just plug in the numbers. Then you can use it over and over again. You can check to see if you got anything wrong. The key to this is to start with adding and subtracting. Can you isolate this thing by adding and subtracting anything? Is there anything that we can add or subtract from this side of the equation first? The idea is to look at this, to view this as one single thing. Since the 2 is multiplied by the a is multiplied by this thing in parentheses, this is all one thing. And this is added to it. Since it's added to it, we can subtract it. Right? So what we do, a lot of people like to do this where they subtract the v naught squared like this. And that's totally fine. I usually do it off to the side over here or above the equation. But if we do this from both sides of the equation, remember if you do something to one side of the equation, you got to do it to both sides. Then on the left side, you're going to get v squared minus v naught squared, and we write that out, v squared minus v naught squared. And I highly recommend you do one step at a time. Don't try to do multiple steps. It just confuses things. These two are going to cancel to give us 0, right? And then we're still going to have the plus 2a x minus x naught. Now, because this is all multiplied, this is three things multiplied together and there's no plus or minus signs in between here. There is a minus sign inside the parentheses, but whenever you have something inside a parentheses, you just consider it one thing. Just call it what's inside the parentheses. Don't think about trying to figure that out yet. Do that, deal with that later if you have to. But we're just going to consider this all one thing, and so this is a 0, so there's like it's not even there. And we only have one thing on the right-hand side, and we have two things over here. Now we have nothing added on or subtracted on to this one thing over here. There's no more adding and subtracting to do. Now we start looking at dividing and multiplying. Is there anything we can divide or multiply on this side to get rid of something on this side? Absolutely. What can we do?
2.
We could divide by 2 over here, right? Which means we'd have to divide by 2 over here, right? So we go ahead and do that. It cancels out the 2's on this side. We're left with this on this side. And that's fine. And then what's the last thing we can do? We can divide by x minus x naught, right? Because it's all one thing. The thing under the parentheses. And divide by x minus x naught over here. And of course it cancels on this side. And we're left with just a over here now. Right? Everything else is canceled out. Now, if you're wondering how do you type that into my open math, that's a good question. You can do it a couple of different ways. You can do it using the math code version, which looks like this. It will look like you'll have the v squared minus v naught squared on the top. Whenever you have something, more than one thing in the top or the bottom of a fraction using math code, you want to put in parentheses. So I usually start by putting in a set of parentheses first, and then I click in between the parentheses and I put in my thing here. So this is going to look like this. V hat 2, that's v squared, minus, and then this one is going to look funny. It's going to be v underscore 0, like this, right? And then you can actually do it two different ways. The way I like to do it is I like to put parentheses around it again. So I'll put a parentheses around that. I'll add another parenthesis out here. And then I'll do a hat 2 on the outside of those parentheses like that. That's my favorite way to do it because I think it's cleaner. But you can also just put a hat 2 after the O. But sometimes that confuses people because they think that's squaring the O. It's not, it's actually squaring the V sub O. But you can do it either way. I like this way because it's cleaner. Once you've done that, then you divide by to get your denominator. And since I have lots of stuff in my denominator, I'm going to put parentheses down there first. And I'm going to do a 2, and I'm going to do a times, and then I'm going to do parentheses again, and I'm going to do an x minus an x underscore 0. And these are zeros, not O's. So these are zeros. So that's how I would code that into MATLAB, or into my open math rather. And that's pretty standard code for any math program. Now the other way that you can do this, is to click in the box and use this arrow button. And this is actually quite useful. So since we're going to be doing a fraction, I'm going to press the fraction button, and then I use my up, down, side to side arrows, or no, it's not working apparently. But I can use this right here. I can just click in there, and then I can put stuff in the top of the expression. And in this case, I don't actually have to necessarily type in parentheses unless it's explicitly required. And what was I can't remember what my answer was, but whatever it was, what was on the top of the answer? I can't remember. We solved for, what did we solve for, A? Okay, so if we solved for A, then it's going to be, oh yeah, so we had the V. So what I would do is I would do V, and then I would, make sure that you use the correct case, because MATLAB, I keep saying MATLAB. It's a different program. My Open Math knows the difference between upper and lowercase. So what I'm going to do is I'm going to do a V and then I'm going to do an underscore. So this is the underscore right here, underscore 0. Oops. Then I have to click in that spot, 0. And then I'm going to come out of that underscore with my thing here. I push that, if I'm inside the underscore, if I push my to the right arrow, the right arrow will take me out of the underscore. And then I'm going to do an upper thing here, and I'm going to square that, put my cursor in there and square it. So there's my V squared, and then I'll come out of it again by pressing to the right. Then I'm going to go ahead and subtract the V. Oh, it's actually the other way around, right? I made a mistake. It's actually V, it's going to be V sub x squared minus V x naught. So I'm going to change that. So this one, I'm just going to get rid of that. And I think you can actually get rid of the whole box just by clicking down here. So if I just delete that box, now it's V squared. And then I'm going to do minus V underscore, and that one's going to be a V naught, V0. And then I'm going to go back here and I'm going to square the V. So that'll be V squared. So there's my V minus V squared in the top of the equation. And the bottom of the equation is going to be divided by 2 times x minus x naught. So I put a 2 down here, put a parentheses, whoa, I put 2 sets of parentheses. Then I'm going to do an x minus an x, and then I'm going to underscore 0 like this. And then you go ahead and press save that, and it will check it. It looks like it says it's a syntax error. Oh, because look, this is V2, 0. It's not, obviously not right, quite right there. So I go back into here, go back into this. I need to go back and fix this 2 and put it into this thing, and then save it. And that's still wrong. It's not quite right. So I come back here and see what I did wrong there. I think what I want to do maybe is to get rid of this one. And maybe it wants parentheses around that. I'll put parentheses around it and then square it maybe. Let's see, how do I do that? As the teacher, I don't use it as much as the student, obviously. Let's put the V underscore 0 inside. Come on, I want that underscore. And then we'll square it and see how that works. And sometimes this is just kind of what you got to do to try to make it work, is try it out and see if the syntax works out. So that one we'll save, see how that works out. Still doesn't like it, why not? You might want it 2 times here. It doesn't like this at all, I don't know why. Did anybody else do it this way and get it right? Let's try V underscore 0. Save. Okay, let's try to do the square first then. I didn't think it mattered which direction, which way I did it, but I'm going to try that first. V squared, and then underscore 0. Sheesh. Underscore. There we go. I can see that it's different now. Come on already. I don't know what it's doing. So it's saying it's V0. Doesn't like that, so let's do it this way. I don't know why it's not doing either one of those. U squared minus divided by 2x minus x0.
Is it because you're supposed to solve for x for that question?
Oh yeah, that's probably why, because I'm solving her problem on this one, right? So if it wants me to solve for, well, still should give me a, it should still show that it's not a syntax error though, I don't think. Well, unless it's got a written into it that if you put the, let's actually take x out of there and see if it lets me do it. Okay, so it's no, still syntax error. Let's try it. Let's try to fix this. Okay, so yeah, maybe. Well, it shouldn't be a problem at all. V minus V naught 2 over x naught. 2 times x naught. I don't know what's going on with this. I have to check the code of this problem. There's something else going on. This is syntax error no matter what I do. Let's just do this. Yeah, that's ridiculous. There's a problem with this. Well, okay, let's try to plug it in using, I'm just going to solve this one really quick and just plug it in using the answer I'm supposed to do. So this one's going to be V, so x squared minus, oh, I know what I did wrong. Was that what you were saying, is that I didn't put in the x's? Is that what you were saying?
No.
Okay, so I'm going to do it again really quick. I'm going to put in V sub, because they don't have a V naught, they have an X naught. Is that what you were saying? That's what you were saying, okay. So yeah, this would be correct. So let's do it again, sorry. I just was not putting in the X's and wasn't even paying attention to that. So let's try it again using this one because I want to make sure this is working for you guys. Now I'm just going to type in some expression because I don't want to waste any more time. But it's, let's say we're doing V sub x0 and then not minus, sorry. So we're doing V and then we do a subscript, and that one is going to be x0 because it's an x0, not just a 0. And then we get out of that and we do a square by pushing this button, and we do a click up in here and get a squared, and then we subtract off whatever V sub x, sub x. This way is just kind of time consuming. And then we put in here a, we do a sub x just for fun. And then we save it and we say syntax okay, because we had all the correct variables. The thing that I was missing was the x and 0. I just put a 0 instead of x0. And I put a v instead of v sub x. But if you put them in that way, it does come out as long as you're using the correct variables. Because if the variables aren't in this equation, they won't be okay in the syntax here. And that's actually the biggest problem that I have with students who ask questions on these types of problems, is they're using a capital V, or it's a V sub 0 instead of a V sub x 0 or whatever. It's exactly the problem that I had, was what most students have a problem with, is how to enter it in. But if you enter it in correctly here, it'll actually show you the code on how to enter it in correctly here, which is kind of nice. So you can see here that they put in the parentheses, the X0 parentheses there. And let's actually go back and look at my version on the whiteboard, because that one, see, I don't have the VX0 here. I should put a VX0, V sub X0 here, and this one should be a V sub X and then squared. So it should look like V sub X squared. That is the same as this. And if you do a V sub X0 squared, that's the same as this. Clear as mud. And once again, I realize that's kind of annoying because you have to kind of learn how to talk to a computer for this. There are computer programs that do this slightly better. Like maybe takes you, instead of a week to learn it or 2 weeks to learn it, it might take you a couple days to learn it, but you pay a couple $100 for that system. It's really the only thing that works better. So, and then what was the next? You said number 8, maybe. Number 8, okay, so now this is actually the same problem as the car, except it doesn't do the rolling along the table part. It's just starting with the ramp. But instead of a ramp, it's a throw of a baseball. So we can see this if we draw a picture. Let's go ahead and draw a picture. So, if we have, in this one we have a baseball player who's standing up, throwing the ball, right? This is my baseball player, and they throw the ball at some angle. All right, is anybody a baseball player here? Angle theta, and the ball goes and it falls down to where the catcher is sitting. So the catcher is lower down to the ground, and the catcher catches the ball, right? There's a difference in height between the throw and the catch. We have this difference in height here, which we're going to call Y, right? We have a distance between the players, which we're going to call X. And X naught and Y naught can both be 0 if you want them to be, so that our initial height is 0 and our final height would be a negative. And our initial X position is 0 and our final X position is however far away the catcher is, right? In this problem, they tell us they're 43.8 meters horizontally apart, and the ball leaves the outfielder's hand at a height of 2.17 meters, but the catcher catches it at 0.65 meters. So we know those two things, and we can actually, they're actually giving us the, they're saying that the height of the ground is 0, so we can go ahead and make the height of the ground 0, just like they're doing. So if we go back to here, and we say that the height of the ground, we say this is 0 height, and this is whatever Y height, and then the height of the catcher above the ground is that's the final height, and this would be our initial height where it was thrown from. So now we know Y0 and we know Y final. If the height of the ground is 0, this is not very well drawn, but now we know those three things. We know initial and final height. We know initial position in X. This is X0 equals 0. And X final equals whatever number they give you for the distance to the catcher, right? So now I know a bunch of stuff. Now, most people get thrown off by this because I say this is the same as the car problem. It is the same as the car problem, but you're not solving for the same things. They've given you different things, and you're going to solve for different things now. One of the things they give you is the distance in x, right? And do they also give you time? Yeah, they give you the time. In part A, they say it takes 2.4 seconds, 2.46 seconds for the ball. So they give me time as well, which is huge. If they give you time in any problem like this, it's usually a really beautiful thing. So they give you some time, whatever it is, however many seconds for your problem. And then the first kinematic equation can tell you how fast the ball is going in the x direction. If you know, and they tell you the angle of the velocity of the ball to begin with, but they don't tell you the velocity of the ball to begin with. But they have told you the x component of the velocity because they told you the time and the distance. So you're going to use time and distance with the first kinematic equation, and once you get that, that's going to give you so time and your x. Let's see. Time and x are going to give you velocity in the x direction. And velocity in the x direction is this component right here, which was equal to, if this was equal to theta, what was the velocity in the x direction equal to in the car problem? It was equal to this velocity vector, which is the velocity that he throws it with, times what? Give you a clue, it's a trigonometric function. Cosine or sine, if it's next to the angle. It is cosine of the angle. Okay? Now I can't remember if we reviewed this or not. I think we did really quickly. But if we didn't review it very well, let's review it right now. Let's see, I think I can go to a new page. No, maybe not. Let's review the trigonometric functions again. If you have a right triangle and this angle is theta, we call this side the opposite side. That's opposite the angle. We call this the adjacent side, A, J, D, J. And we call this the hypotenuse. And this is just to remember what these functions are. And there's this mnemonic they call it, right? For remembering this, it's ch4a. ch4a. Sounds like some kind of Native American name or something. ch4a. But it stands for sine, opposite, over adjacent, over hypotenuse, rather. And then cosine, adjacent, over hypotenuse. And tangent equals opposite over adjacent. And these are the three functions and their ratios that they're associated with. So if I take the sine, oh goodness, sine of theta in this thing is equal to the length of the opposite side over the length of the hypotenuse, or the length of the longest side. The cosine is the length of theta, is the length of the adjacent side over the hypotenuse. And the tangent is equal to the adjacent side, or the side next to the angle, over the side opposite the angle. Now, if you have the angle, if you know the angle, you can calculate this ratio just by plugging in the angle into the equation, and that's what we're using it here. That's how we're using it here. We know what the angle is. They tell us the angle is whatever degrees. We plug that into our calculator, get the cosine, multiply it by the hypotenuse, and that gives us the adjacent side. It's like solving this equation for the adjacent side by multiplying both sides by the hypotenuse, right? And that's where this equation comes from. And then once you know v sub x, now you can calculate v by going back to this cosine equation. And you want to calculate v, which is the hypotenuse side, so you solve this equation for the hypotenuse side. Or you solve this equation for v. You take v sub x and you divide by the cosine of theta, and you will be able to calculate what v is. Once you can calculate what v is, then you can calculate what vy is, because vy is equal to v times sine theta. So then you can plug in the V that you just calculated from this one, plug it into this one, and get Vy. Once you have Vy, then you can use the kinematic equations in the y direction to calculate how long it'll be in the air from your initial Vy velocity, and your final position, which is going to be this final position, your initial y position, and the acceleration, which is in the y direction, negative 9.8 meters per second squared. Gravity. So you're using the same equations, you're just solving them for different variables in this problem. Same equations as you used in the car problem, but you use them in the opposite order. Instead of using the y equations first, you use the x equations first, and instead of solving for the distance, you're actually going to solve for the time. Or actually, instead of solving for the distance, you're going to solve for the velocity in x. And then you use the velocity in x to get the overall velocity. Then you use the overall velocity to get the velocity in y. And then you use the velocity in y on all the stuff they've given you to finally calculate how far it, what do they want you to do? I don't know what they want you to calculate finally. How long you, something, I don't know, something. Whatever they want you to calculate, they'll use it to calculate that. That ain't making it up. So, same kind of problem. Now, if you're not quite there yet, working on it tonight, make sure you email me. I can't promise you that I check emails late at night. I'm not very good at that these days. I'm trying to get to bed earlier and wake up earlier because I'm trying to be healthier because I'm getting old. But I will check them tomorrow, and we can answer any questions you have tomorrow if you need to. But certainly, get going on those. Does anybody else have any questions? Did anybody else hear any questions? Any more questions for chapter 3? Brittany, did you have any more questions for chapter 3?
Not that I can think of right now.
Okay. So make sure you get those questions to me as soon as possible. We now need to see if we can get started a little bit on chapter 4. Let's see here. I'm going to go back to this really quick. Sorry, I have to zoom. I have to go through my grade page really quick, so I have to block everybody out so nobody can see the grades. Okay. It's looking like most of you are mostly done with chapter 3, so that's a good place to be right now. Let's move on and start chapter 4. If we can finish up chapter 4, can't remember how many sections are in chapter 4. 8 sections. So if we can finish up chapter 4 today, that's actually a really good thing for us. And that will actually get us, and if we can get mostly done with chapter 4, that's even good. Because then our lab tomorrow is all about forces. So let's go back to here, and let's go to a new place here. Okay, so chapter 4. So far, what we've been learning is essentially the physics that was done, all the physics that was done before the 1600s. That was the physics that was done by Galileo and many great physicists and scientists and philosophers, but it was all done 400 or 500 years ago, a long time ago. In fact, it was even done, it was 400 or 500 years ago. So it's old physics. Now we're actually going to enter into the 1600s. And this is widely regarded as really what physics is all about. If we if we're talking about classical physics being the physics that happened before the 1900s, before the 1900s, before 1905. So classic physics really took hold right about this time with this man named Newton. And Newton was mostly responsible for the understanding of how force makes things go. So we've learned about how things go, with velocity, acceleration, displacement, all that stuff. But this is really, why do they go? Why do they accelerate? Why do they turn? Why do they go in a straight line? And Newton was able to write a book about this. He wrote this book, and this here is a copy of it, actually. This, I believe, is one of the original copies. 1687 it was published. Philosophiae Naturalis Principia Mathematica, the natural philosophies and principles of mathematics. And it's no wonder that we do a lot of math and physics. At the same time, Newton also invented the idea of what we call calculus. And so calculus was important. It was done simultaneously with this because it was necessary for it. We're not going to make you do the calculus, but we'll talk about some of the calculus from time to time, the importance that it played. But essentially what he did is he took observations. Galileo spent a lot of time looking through telescopes, looking at the stars, the movements of the planets, and mostly planets actually is what Galileo did. And he was looking at the planets and how they moved relative to each other. And he wasn't the only one. There were many people, many scientists that were doing this. Galileo was just one of the more famous ones. But they were trying to figure out what made the planets do what they did, because planets behave weirdly in the sky. They're strange. They have very strange behavior. And Galileo actually spent time in jail because what he discovered is that the planet's movement makes no sense unless we consider the sun to be the center of the solar system, right? And before that, it was the Earth was the center of the solar system, and this was literally a religiously held belief. And so the Catholic Church put him in prison for saying that the sun was the center of the solar system, and others. He wasn't the only one. But by the time Newton came along, that was accepted, and Newton was able to take those observations and actually create mathematics that described those motions and predicted other motions. And that was amazing stuff. The science of how forces behave, we call dynamics, and sometimes we call it mechanics or dynamics mechanics or whatever. But dynamics means movement, so this is the study of forces and how they make things move. But we're going to start off with some very simple ideas. One of the most simple ideas is the idea of the force. What is a force? Well, a force is a push or a pull. It's that simple. Something that pushes or pulls something, right? And we have this little drawing here from above, these 3 ice skaters, and you can tell they're ice skaters because there's these scratches on the ice below them, right? So we have these 3 ice skaters, 2 in pink, 1 in blue, and the 2 pink ice skaters are pushing on the blue ice skater. One of them is pushing the ice skater to the right. The other ice skater is pushing the ice skater upward on our screen, right? And we have the force 1 from the right, force 2 from the bottom going up, and it creates this vector addition of forces, where the total force will be upward and to the right according to vector addition, just like we did vector addition with displacements or velocities or accelerations. These forces add together just like any other vector. So forces are a vector thing. They're a vector entity where they have both direction and magnitude, or strength and direction in particular. Magnitude is the word we often use in physics for the value of a vector or how much of something you have. And then, of course, the direction is self-explanatory. This, when we see something like this in physics, we often represent it using something called a free body diagram, where the object that is feeling the forces is represented by a point or some other similarly simple thing. And the forces are arrows pointing away from that point in the directions that they should, with lengths that represent the strength of the forces. So in this case, these two forces are about equal. So the lengths of the forces are about equal, but they're in different directions, so they're pointing in different directions. If force 1 was twice as big as force 2, then the vector representing it would be twice as long as force 2. And we call this the free body diagram. We often call this a force diagram or just a drawing representation, whatever you want to call it. Here's an example of a force that has been studied a lot. This is the spring force. So if you have a spring connected to something and you pull on that spring, so in this case we have this massive object on one end and we have a handle on the other end, so the person that pulls on the spring pulls on the handle. The mass on the other end, we'll say that it's bolted down or glued down or whatever, nailed to the wall. And as you pull on the spring pulls back. It's called a reactive force. So whenever you pull on a spring, you feel some resistance, the spring pulling against you. As you try to pull it one way, it tries to pull you back the other way. So this is often called a restorative force or a reactive force. And it turns out that the more you stretch it, the more the spring pulls back. I don't know if you've ever experienced that with rubber bands or springs or whatever else. Things that have this kind of spring nature will pull more the more you pull on them, to a point. Eventually you can pull so hard that the spring loses its springiness and it doesn't pull back at all, right? So this works fairly well in some situations, and it's a very common force. Can anybody think of any other common forces that are pushers or pulls that aren't mentioned here? Like this is just people pushing on each other. This is, a spring, somebody pulling on a spring. Can you think of any other forces you've experienced or that you know of in your experience in life? There's an obvious one that we've already talked about a little bit. You feel every day, every moment. Gravity. Gravity is a force. Gravity is a really weird force because there's no contact necessarily. With the ice skaters were contact between the hand and the ice skater, right? And that created this push. With the spring force, you pulled on the spring, you stretched it out, so there's some kind of physical thing. But with gravity, that's not necessarily the case. Gravity is, their contact is the reason that we feel the gravitational force, but it's not the reason that it's there. So if you're out in space, orbiting the Earth, you still feel the gravitational force of the Earth still acts on you if you're orbiting the Earth. But you don't feel it. You feel weightless when you're in orbit. Does anybody have any guess as to why that is? Why I say you don't feel it even though it's there? What makes us feel gravity here? Why do we feel like we weigh something? How do you weigh yourself? I found the two ugliest scales I could possibly find. This is my favorite one, the fuzzy scale. This was my childhood, 1974, 60s and 70s, avocado green, fuzzy appliances. This is just so my childhood. But don't look at the scale because it'll be embarrassing. But why is it we step on something when we weigh ourselves? What's that doing? Why do we have to step on something? Is there any other way to weigh a person? Can hang from something, I guess, right? Well, the reason we have to step on the scale is because we have to put it between us and the Earth. Have any of you ever felt weightless before? Have any of you ever been on a water slide that shoots you out over the air, or a roller coaster that goes in a loop, or been in an airplane that suddenly drops 50 feet in a storm and you feel that stomach? Been in an elevator? Anybody want to lose weight today? You can go to the elevator, take the scale with you, get in the elevator, push the down button, you'll lose weight. What's the problem with that? You'll gain it again at the bottom when it stops, right? And why is that? Because the floor is falling out from underneath you when it starts, and then it gets in your way, it stops you at the bottom. The reason we feel our weight is because we're in contact with the ground. If we're not in contact with the ground, we don't feel weight. If you jump out of an airplane, you don't feel weight. If you jump off a mountain, you don't feel weight. You know, if you've ever been skiing, you know you feel weightless when you go off a little jump or a big jump, right? You feel weightless. And that's weightlessness is not the absence of gravity. It's the absence of something that's in your way that stops you from falling, right? People that are in orbit around the Earth are literally falling around the Earth. They're just going so fast sideways that when they fall over the edge. And then the next time they fall over the edge again, and they're continuously falling over the edge of the Earth, right? Over that, around the horizon of the Earth. On the Earth, we're not going very fast. We're not going fast enough to fall over the horizon. So we fall and we hit the Earth and we feel it. We feel our weight, right? Our weight on the moon is different because the gravitational pull is different on the moon. It's about 1/6 of what it is on Earth. Another really quick way to lose weight, go to the moon, right? 2 weeks, you could lose like 200 pounds. I could lose 200 pounds, but no, none of you could lose 200 pounds in 2 weeks, but I could. And it would be, no effort except going to the moon. So gravity is another one of those forces. There are other ones as well that are out there. Magnetism is one that we don't, we've all experienced. We have like these magnets and they're stuck to this board, but you flip them around and you can get a repulsive force and an attractive force. So that's kind of interesting. Right? How many of you have ever had your hair stand up in an electrical storm? I bet you have. Long hair, you can always feel it. You're like, oh, have you ever been on a trampoline? Your hair stands up? Yeah, my girls with long hair, when they're on the trampoline, they're just like halos, right? That's another force, and it's a force that is both, it's like magnetism. In fact, it's directly related to magnetism. There is no such thing as electrical force without magnetism force. They're always tied to each other. Magnetism force is much less noticeable, but electrical force can both be attractive and repulsive. It can be both. So, lots of forces out there that we experience, but it turns out it's actually less than we imagine. We think about this, and we talk about this a lot, but there are actually fewer. And I'm going to jump to the end of the chapter because I kind of like this idea at the beginning of this chapter. It turns out there's actually only 4 basic forces, and here they are. The gravitational force, we're very familiar with, but we know very little about. It is one of the most mysterious forces. It is only attractive, and it's the only one of the 4 forces we know of that is only attractive. What is going on with that sound? Sounds like feedback, but I don't know where it would be coming from. What is today? Monday? That's got to be coming from outside, doesn't it? What's that? Could be. Yeah, it could be something. I don't know. Is that? Can you hear that sound? Is it bugging you there? And
I can barely hear it.
you can barely hear it. Okay, so if it's not bothering you, I'm not going to worry about it. That means it's not carrying over because it's not too loud here. Anyway, I was just afraid it was like blocking out the sound. So anyway, the gravitational force. It has an infinite range. Gravitational force holds the universe together, literally. And not only that, but we've just recently discovered that gravity makes waves in the universe. So this is really interesting. It was just last year. They actually have this huge device. It's like miles long. They have several of them now. But what they do is they measure how space changes with gravity. Space itself actually changes. Like if we could perceive it with our eyes, this room would like get smaller and then bigger because of gravity. But the changes are so small that we can't perceive it with our eyes at all. And our eyes aren't even designed to perceive that kind of thing. We would have to have gravitational eyeballs or something. But they were able to figure out a way to detect it using some lasers and some very, very, very long equipment. And they were able to essentially detect a gravitational wave that traveled from millions of light years away and traveled all the way to Earth over the millions of years and made this little bubble in it, and they've actually detected several of them now. Something that Einstein predicted 100 years ago, well, not quite 100 years, but almost 100 years ago, and it actually happened. But it's only an attractive force, and it's caused by mass. Mass is the thing that creates this attractive force for some reason. But again, it's not really well known exactly why. We're still learning about it. It's very much a mystery. It's very much the most common force we're familiar with throughout history, but it's like the most elusively mysterious one, which makes it kind of interesting. And each one of these has a particle associated with it. The graviton has never been observed. We don't know what it is. We don't know much about it, and we've never been able to detect it. But we call it the graviton. We assume that it's there because all the other forces have a particle associated with them. This particle, the graviton, would be a particle that has no mass. The electromagnetic force is another very common force in our experience, but we didn't really understand much about it until recently. For example, everything that you touch, everything that you feel, with almost all of your senses, actually, I had to think about that for a second. Every one of our senses, if you sense a force, your hair on a trampoline, you're pushing against this, cold air, tastes, all of these things are directly related to the electromagnetic force, all of them. And it has to do with electrons pushing against electrons and protons attracting each other, because electrons repel each other and electrons and protons attract each other. And then there are other particles out there that you can consider as well, but pretty much that's what it comes down to, is that pretty much all matter is made of these three particles, electrons, protons, and neutrons. And neutrons have no electrical charge, and protons and electrons have electrical charge, and all the interactions between them create forces. Pushing forces, touching forces, smelling, chemistry, all of chemistry. So smelling and everything else, light, they're responsible for light as well. The carrier particle is the photon, and photon is a light particle. So everything that you see is due to this electromagnetic kind of thing. So this is responsible for almost all of our human experience, electromagnetic force. Then there's this weak nuclear force, which is responsible for things like radiation. So radiation is something that's very common, but we didn't know much about it, again, until the last 100 years. Radiation was discovered 120 years, 230 years ago, but we do know a lot about it, even though we just recently discovered it. And then there's this one, the strong nuclear force. This one is what holds matter together. So a proton is held together by something, and that's what it is right there. It's called the strong nuclear force. The nucleus of an atom is held together by the strong nuclear force. And this one is by far the strongest force. This is what makes an atom bomb do what it does. When you break an atom and you break this force, you release just a tiny bit of energy. You release essentially, you create a tiny bit of. You take a tiny bit of mass and create energy, pure energy from it. A tiny bit of mass, like a few grams, will create an atom bomb kind of energy. That's how it just takes a few grams of matter, turn it into pure energy, makes a bomb that can destroy a city. So that's a lot of energy, a lot of force right there. The electromagnetic force is 100 times smaller than that. That's our force when we're touching things, feeling things, seeing things. 100 times weaker than the strong force. The weak nuclear force, which creates radiation, is like 1 trillion times weaker. It's 10 trillion times weaker than the strong nuclear force. And the gravitational force, which we consider to be really strong because it holds planets and orbits and everything, it is 10 to the minus 38. It's I mean, there's not even a name for that. It's like such a tiny number. It's so much weaker than the force that holds matter together. So these are the different forces that we deal with. Now, what we're going to deal with is pretty much going to be in this realm and this realm. Pushing things, pulling things, and then the gravitational force pushing or pulling on things, right? We're not going to really deal with these. These are second semester things that we deal with a little bit. Not much, but a little bit. But these are the ones we're going to deal with in this class for the most part. And the study of all those forces is really what physics is all about. In one way or another, we're trying to study how matter interacts using those forces. Newton had no idea about those four forces. He just knew that there was force, and he was just studying it. Nowadays, we know a lot more. So let's go back to Newton. We'll rewind 400 or 500 years, and go back to Newton. And what Newton wanted to do is he started to characterize these forces. Extremely important in science to understand what things are doing first. What's happening? That's the first question you ask. And then the second question you might ask is, why is it happening? But that also might be the ninth question you ask. You might ask a lot of other questions in between. So these are the answers to what is happening around us in the universe. What Newton observed, he called these his laws of motion, and the first thing that he observed was that if something is at rest, or if it's in motion, it will remain in motion at a constant velocity, or it will remain at rest, if it was at rest to begin with, unless you make it do something else, unless it's acted on by some kind of force. Now what they say here is a body's at rest remains at rest, or if it's in motion, it remains in motion at constant velocity, which means constant speed and constant direction, right? Unless acted on by a net external force. Net force means that the total amount of forces you add up, you'll have some leftover force that's acting in some direction. And then external means is that it's acted on by something outside of the object itself. The object can have forces going on inside of it, but those are not considered external forces, and they don't affect the motion of an object. So one way to describe what this is about is if you throw a person out into space with their spacesuit on, they actually will just keep going off into space as long as there's no gravitational field if there's just empty space, a universe with nothing in it but this spaceman. You throw them off into space and they can do all they want. Wave their arms and tuck their body and do everything else, but their direction is still going to be going in one direction the whole time. Because nothing externally can act on them. Only internal things. They can only do internal things. They can roll, they can change their position and everything else, but if you plotted their position in space, it'd be a straight line forever, because nothing is going to act on them. That's that net external force that has to act on them. And of course, if they're just sitting there, they're not going to do anything either. They can kick their legs out and everything else and try to do everything, but they're sitting there will just be sitting there in the end, right? This is something that all astronauts have to learn when they go to the space station. Every once in a while, they're in the space station and they're working on something, and they discover that they've drifted somewhere away from something that they can touch, because there are some bigger modules in the space station. And then all of a sudden, they can't get anywhere. And so they actually have to take a big breath and like blow in one direction, because that actually exerts a force on the air outside of their body, and then it will actually rotate them. It actually makes them spin towards the other wall. So it's something that you have to learn in the space station, is to never ever get yourself too far away from something to hang on to, so you can push yourself somewhere else. You don't want to get stuck in the middle. It's a rookie mistake that they make. Anyway, so Newton's first law of motion. I like to call this, things tend to keep doing what they're already doing, right? And there is a way to talk about how much something wants to keep doing what it's already doing. And we call this the inertia of the object, and it is directly calculated by the mass. Something that has a lot of mass has the tendency to keep doing what it's already doing more than something that has less mass. That's also one of the consequences of that's one of the observed things from Newton's first law. Now, when we talk about laws in physics, we're talking about things that have been observed to be this way all the time. This has always been observed to be this way. Nobody has ever observed it any other way. This is not something that we've proven. It's not something that's an absolute truth in the universe. It's something that has been observed over and over again, and it's always been observed to be this way. So it's more like we've only seen it this way, so we're going to assume that it's this way all the time, right? Until we observe it otherwise, we're going to assume this to be true. It's an assumption. And all of physics is based on this assumption. What happens if we observe this to be untrue at some point? We'd have to change physics. We'd have to change the science. And guess what? That has happened. It has happened many times. One of the laws of science that is used very commonly in chemistry is what is called the conservation of mass, is that mass can neither be created nor destroyed. In 1939, before 1939, Einstein predicted that wouldn't be true. He proved it theoretically that mass could actually disappear and you could create mass as well. And then in 1939, they actually made it happen. In 1939, they created the first nuclear reaction, and they actually made mass, disappear. It became pure energy, had no mass anymore. And that's how nuclear reactors work. That's how nuclear bombs work. And that law had to go out the window. They still use it in chemistry because for what chemists do, it doesn't matter. Chemists are never going to make a nuclear reaction happen. They can't do it in their laboratories. It's impossible. You have to have a lot more energy to make a nuclear reaction happen. But that law is no longer true. And there are many laws that have been struck down, especially in the 20th century. Because we observe, and then all of a sudden we observe something that doesn't obey that law, and we try to make sense of it, and eventually we have to make a new law. So there's our first law, which is the first law of, not Newton's first law, the law of inertia, it's often called, or things keep doing what they're already doing. Now the second law. The second law of Newton came from observing the effects of force on motion. How does force affect motion? And it's important for this to be able to understand what a system is defined as in physics. So we often call this the system of interest. In physics, you need to know what you're talking about, what is the thing that you're interested in, and what is outside of that thing that you're interested in. So a good example is this kid in the wagon, right? If we're talking about the kid and the wagon together as one object, then anything that pushes on the wagon or the kid is going to be pushing on our system. So in this case, we have two forces, one force from the kid in the pink and one force from the kid in the green and the purple here. This girl here is pushing on the back of the kid in the wagon. This person here, girl or boy, I don't know, is pushing on the wagon, right? But since the kid and the wagon are both part of our system, then this is our system in our free body diagram, this point, and there's two forces pushing on it in the right-hand direction. There's also the weight of the, excuse me, the weight of the wagon plus the weight of the kid. So this is the weight of the entire system that's being pulled down towards the center of the earth. And then they have a normal force, they call it. This is the force of the earth pushing up on the wagon. That's necessary. Why is that necessary? What happens to this wagon if the earth doesn't push up on the wagon? If the earth isn't here, if this is like the edge of a cliff right where these kids are standing, what happens to the wagon? Wagon falls, right? The earth has to push up on the wagon because weight is pushing down on the wagon. Gravity is pushing down on the wagon, right? So you have to have another force that's going to stop that force from making the wagon fall through the earth. So they call that the normal force. We'll talk more about that later. And then we have a frictional force, which frictional forces always act opposite the motion. So if this wagon is moving forward, which it is, then the friction will act backwards and it will kind of slow down the wagon a little bit. And here, this is our free body diagram for that system. Now, what if we have a different system? What if we define the child as the system, not the wagon? Let's see. Is that what they're doing here? Yeah, that's not exactly what they're doing here. But let's say that let's imagine that we're just saying that the child is our system of interest and not the wagon necessarily. Um, if the child is our system of interest, then the child is still going to have some weight. The normal force here will be the normal force of the wagon pushing on the child, not the earth pushing on the wagon. This would be the normal force of the wagon pushing on the child. You'd have the force of the adult pushing on the child still, but then you would also have friction of the child sitting in the wagon, because there's friction between the child's butt and the wagon, keeping the child from sliding. If there wasn't, the child would slide around in the wagon all the time, right? And even if there wasn't any friction between the surface and the child, there would be friction of the feet on the end of the child, or there'd be a pushing force of the feet of the child on the front of the wagon, or their back against the back of the wagon, or whatever. So we essentially would just pretend like the wagon wasn't there and draw another free body diagram. And with what system you use depends on what you're trying to solve for. You want the thing that you're trying to solve for to be in your system somewhere, or to be acting on your system, one or the other. And it's not as maybe convoluted as it sounds. It'll be pretty obvious what the systems are. But it's important to understand it so that you know what forces are external and what forces are internal. For example, if a problem tells you how hard the child is pulling on the handle on this wagon, does that affect the speed of this wagon? Well, only if the child is external to the wagon, right? So since the child is internal to the wagon, the child pulling on the wagon's handle is not going to affect the wagon's speed. It's not going to affect force on the wagon, because that's an internal force. We want to know what things are external and what things are internal. So sometimes it can be a little bit tricky to make sure that you assign those correctly. Anyway, what does Newton's second law say then? Once you've defined your system, once you know where the forces are acting, external forces, where they're acting on a system, what Newton discovered is that the acceleration of the system is always proportional to the net force on the system. So if you increase the force by double, the acceleration will double. If you increase it 10 times, the acceleration will increase 10 times. And that those things are in the same direction. And that's why they use the boldface. In this book and most books, boldface means vectors. So the acceleration vector is directly proportional to the force vector, which means not only do they increase and decrease at the same rate, but they also are in the same direction. So if you apply a force to the right on something, it will accelerate to the right. A net force. It has to be a net force. Remember that net means you add up all the forces, and it will have some force left over pointing in some direction. Another thing that he discovered is that the acceleration is inversely proportional to the mass. Now, in this case, mass has no direction, so this is not considered a vector proportionality, even though they did put a boldface A here. They shouldn't have. That should be a lowercase a, but the acceleration is going to be inversely proportional to the mass. So if you have more mass, you have less acceleration. And this is actually very easily understood in what I call the mosquito meets truck scenario, right? If a mosquito runs into a truck on the highway, right, which one gets the worst end of the deal? The mosquito, right? The mosquito ends up as just a little stain on the windshield. And that's because the truck has a lot of mass. Mosquito doesn't have a lot of mass, right? Those mosquito essentially gets accelerated so quickly that their acceleration makes one end of their body meet the other end of their body very quickly, right? The acceleration is traumatic. The truck doesn't get hardly accelerated at all. The mosquito pushes on the truck a little bit. In fact, they actually calculate, like people who are trying to save money with driving cross country, they actually know how much money you will spend on gas killing mosquitoes, that kind of thing. People actually calculate that. And that's actually why they shape their trucks the way they do. One of the reasons that trucks are shaped the way that they are nowadays is to make bugs not hit the truck as much. They'll go around the truck. And so they hit this, they get into this like this air thing, and they, instead of going right into it, they go around it a little bit, get hit less.